This is the fifth lab of Physics 1. It is about a skydiver who jumped from the stratosphere of the Earth. The scope of this lab is to analyze the physics of the experiment. Please pause the video to read all the details about the drag force and the point particle system. Even if for this lab there is not the limit about the length of the video, I will try to compress it as much as possible. This is a list of some assumptions about the gravitational acceleration, the atmosphere composition, the drag force coefficient behavior, and the dependency of the terminal speed from the altitude. This is the physics model with the reference system and the unit vector j hat. There are two forces acting on the object: the drag force that is pointing opposite to the motion, and the gravitational force, that is the weight, that points towards the center of the Earth. The assumption is that the drag force is turbulent. This is the Newton's second law model. The F net is equal to the vectorial sum of the all forces acting on the object, that are the weight and the drag force. This is to underline that positions and altitudes are different. The positions are measured from the reference system, whereas the altitudes are measured from the Earth's surface. Therefore, the altitudes are positive, whereas the positions are negative. Note also that the experiment values are available only for the most important part of the free fall and for some particular instance. This is the velocity graph provided by the organization. We can see the terminal velocity dependency from the altitude, the experimental vertical speed of the skydiver, and the theoretic speed of a falling object in absence of drag forces, that is, the red line. The experimental speed shows that there was not drag force at the beginning of the fall due to the low air density. Moreover, it shows that the vertical speed continuously changes and its slope changes more when the object encounters discontinuity in the air density variation. As discussed in the next slides, the curve can be linearized considering some time subintervals. I identified 12 subintervals in which I found 12 different drag force coefficients using the Python model. This table shows the subintervals. Some of those values, the black ones, were available in the experiment documentation. The red ones come from the analysis of the experimental velocity curve shown in the previous slide. In this one and in the next two slides, there is a summary of assumptions and physics analysis. It is important to say that even if the object velocity tends to maintain the terminal velocity, it cannot stay constant because the terminal velocity is not constant. I had to guess the mass of the object for the model. I assumed a mass of 95 kilograms. I modeled the negative work done by the drag force using the definition, that is, work equal drag force scalar product delta position. The equations are available in the Python code. The drag force coefficients have been found using a trial and error procedure by comparing the velocity of the object at the end of any of the 12 subintervals with the experimental velocities. These position plots show a very well match between the model and the experiment. There is only a discrepancy of about 4.5% at the end of the experiment. It might come from the not well detailed linearization of the last subinterval that lasts 60 seconds using the same drag coefficient. The velocities match very well. I also highlighted the 12 subintervals in which I linearized the experimental velocities. This is the model simulation of what we have just discussed. On the right we can see the object position and the vertical speed, whereas on the left we see the forces and the object motion. The F drag and F net behavior depend from the change of the drag coefficients as previously discussed. The fast increase happens at the beginning of each subinterval when the drag coefficient is updated. At the end of the simulations, the speed becomes constant because it reaches the terminal speed. I'm going to move forward up to the end, and I encourage you to see the whole simulation running the Python code. And this is the print of the positions, the altitudes, and the drag force coefficients. These are the forces and velocities equations before and after the maximum vertical speed. On the left, the drag force is less than the weight, so that the object increases its velocity. On the right of the discriminant line, the drag force is greater or equal to the weight, so that the Fnet is pointing upward or it is zero, and the velocity must decrease since it is greater than the terminal speed. The falling object is a terminal speed follower, because the terminal speed is a point of stable equilibrium for that system. The object follows the terminal speed because the drag force does a negative work on the object at the expense of the kinetic energy. We can apply the energy principle at the system constituted by the object plus the Earth. Since there are not interactions with the surroundings, the delta total system energy is equal to zero. We will see in this simulation that we need to introduce the negative work done by the drag force, or the equivalent delta thermal energy, to have the energy principle satisfied. Note that the delta thermal energy is positive, and therefore the system will increase its temperature. The positive delta thermal energy compensates the reduction of the kinetic energy of the object. There was also a temporary rotation of the skydiver, whose effect is described in the slide. Here we have some graphs about the energy. In the top graph, the delta total system energy, that is the green line, is not zero, because something is missed in the equation. That means that the kinetic and the gravitational potential energy are not the only energies in the system. In the bottom graph, I introduced the delta thermal energy, that is the green line, so that the delta total system energy, that is the yellow line, becomes zero as expected. The delta thermal energy has been calculated starting from the negative work done on the object by the drag force. It is rather surprising that a drag force modeled as a quadratic function of the velocity does such a perfect work on the object so that the energy principle is satisfied. Note that when the speed becomes constant, starting from time equal to 135 seconds, the delta kinetic energy is equal to zero, whereas the delta thermal energy and the delta gravitational potential energy are constant, but they are not zero. It means that the drag force continues to do a negative work on the object in order to cancel the gravitational potential energy that would otherwise become kinetic energy. This is the model simulation of what we have just discussed about the energies. It is an interesting simulation where we can see the energies, the forces with the Fnet, and the object motion. Since the whole simulation lasts 4 minutes, I'm going to move forward up to the end, and I encourage you to see the whole simulation running the Python code. So I'm moving immediately up to the end, and we can see the graphs of the energies. This is a physics comparison between an object falling through the air with layers of different densities and a rock that falls through the air and impacts the water, that is a substance with a much greater density. This is the results summary plus a table that shows the 12 time subintervals with the turbulent drag force coefficients. This closes my analysis. Thank you.